Hello everyone. Today we're looking at showing two triangles are congruent by looking at certain combinations of parts. In the past, in day 4 of our notes, we were looking at showing two figures were congruent by looking at every pair of corresponding parts to be congruent. You had to check every pair of corresponding sides, you had to check every pair of corresponding angles, and if each of those pairs were a congruent pair, then that meant the figures as a whole were congruent. Well, it turns out there are a few shortcuts, and we're going to be learning about those today and in the days to come. We're looking at some combination of parts, not all of the parts, and we're going to see what works and what doesn't work. So you'll recognize that this is listed as day 6. What happened to day 5? Well, that's kind of what this little demonstration is about. This was our day 5 demonstration we would have done in class. And so let's take a look at this concept before we get back to the notes. So here I have on just tracing paper a triangle by the name of triangle ABC. It has 3 angles, it has 3 sides, and I'm going to explode it apart. I'm going to pull all those sides apart so that each part has each part is on its own piece of tracing paper. So for example, when I explode that apart, the right hand side, which is segment BC, it's going to drift over here, and that's going to be its own little piece. The bottom part of the triangle, that's segment AB, we're pulling that apart. And segment AC is also separated from the rest. Now that's also true for all the angles, because technically there are also 3 angles. And remember, an angle has a side that exists of array. It's not set to that particular length. Only when you combine the size of that angle along with the side of that angle, only then do you know how long the angle side needs to be. But without that side information, it's just angle A, and technically those angles go on forever. Alright, so we would have an angle A, an angle B, an angle C. We pull all that apart. So what we're going to do is take a look at just the combination of 3 sides. We're ignoring the angles for today, and we're asking the question, if we reassemble these 3 sides back together again, are we guaranteed to get the same original triangle? Or if I reassemble the parts, is it possible that I could come up with a triangle of a different size or different shape? Because if I can reassemble these 3 sides and I get the exact same original triangle every time, then that means we have found a way to prove triangles can be congruent by focusing on the sides. But if I assemble these 3 sides and I get a different shaped triangle, well, then the true triangles would not be congruent. So let's start off with segment AC and segment AB. Now when we are bringing these 2 parts back together again, if we have a point called A, and I realize it might be hard to see that through the tracing paper, but there's the point called A. If we have these points called A, we can't have A in 2 separate spots. Point A refers to a location. They have to have the same location, so we have to bring the endpoint A together again. But because I don't have an angle, there's no indication where this side should be placed relative to the first side. So if I just use my marker here to kind of represent where that third side is, we could make this an obtuse triangle. Or if I rotate this further in, I could make this a right triangle. Or if I rotate it really close to the original, we could have an acute triangle with a very small angle at A. So because I'm focusing on only the 3 sides, I have no idea what the angles are supposed to be. But it turns out we only have 2 sides. We need to bring that third side in, don't we? So let's bring in that third side. Now again, we have to match up these points. So point B has to match up with point B. When I do that, the C's are in different locations. Again, with all the layers of tracing paper, there's the first C, there's the second C. We don't have the C's in the right spot, so we need to bring it closer to each other so that the C's are in one spot. and the B's are in one spot, and the A's are in one spot. This is rather fiddly, trying to get all of the pieces of tracing paper lined up, but I think I've got it. I think I've got the A's with the A's, and the B lined up with the B, and the C lined up with the C. Now, so I brought it back together. I didn't have any information about the angles. I only focused on the lengths of the sides and connecting endpoints with other endpoints. And the question is, do I have a triangle that is exactly the same shape and size as the original, or did it make a different size and shape? So here's the original triangle. So yet another layer of tracing paper. We put that on top, and as best as we can see, it does look to be exactly the same. So we have found our first shortcut. It turns out that you can have two congruent triangles if you just focus on the three sides and you can ignore the angles. So what that means is we don't have to find every pair of corresponding parts to be congruent. We just need three pairs of sides. I'll come back up to the top in a moment. That's what we're seeing right here. This is the summary. We call it the side congruence postulate, and we're going to abbreviate that as SSS. And the idea says if three sides of one triangle are congruent to three sides of a second triangle, then that's enough for us to say the two triangles are congruent. So the sides are already marked. If segment AB is congruent with segment RS, and segment BC is congruent with segment ST, and segment CA is congruent with segment TR, if we know all of that information, then we can say the triangles are congruent. And here's our congruence statement saying triangle ABC is then congruent with triangle RST. That's the big idea for today. However, before we go on and look at the examples, we need to back up a bit and just explore for a moment, would this idea of just looking at the sides work for some other shapes? So here, this is talking about the little demonstration I just did, where we saw that two triangles are congruent if three sides of one triangle are congruent to three sides of another triangle using that pattern. And this is the question I'm posing to you now. Does it work for all figures? So let's compare some quadrilaterals. Okay, so let's imagine that we're going to draw a quadrilateral here, and we're going to use sides of length 5, 7, 9, and 11, and I'm just going to write the numbers down, and I'm not measuring it specifically, so we'll just kind of make a side look longer than the other, and we'll have an idea of what its length is by putting the number on the side. So let's start off with drawing a trapezoid, and let's put the big side of 11 on the bottom, and then I'm going to put the side of 7 on the right, so we'll make that little right trapezoid. And then here's the shortest length of 5 at the top, and then on the left side there's a slanted side of 9. So using the same idea as what we just did with the triangle, if we were to take this trapezoid and pull it apart so that we just had 4 sides, and we ignored all the angles, and then we brought those 4 sides back together again, could you make a shape that is different than the original? We're not asking could you make the same shape. Of course you can make the same shape. The question is, can you make a different shape? And we can by just replacing these two sides with each other, just switching them around. So let's compare that with this shape again. So the long side of 11 is on the bottom, and there's the length of 7 on the right. If we take the length of 5 and the length of 9 and we switch them around, well then my short length of 5, it's not going to reach the whole way across. It would have to be something like this. And then the length of 9, which is longer, will be something like that. Now what you want to observe is not just the sides, but the angles between the sides. If you were to compare these angles, it turns out these angles are not congruent. we reassembled this trapezoid with these four sides. It's not a trapezoid anymore, and we've created two different quadrilaterals. In other words, these are not congruent. So this pattern of side, 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 where you are guaranteed to get congruent triangles, only works with triangles. If you have other shapes, it does not work. So let's just summarize that right down here. By changing the location of two sides, the angles have also changed. And because the angles have changed, now when I mean the angles have changed, I don't mean the angles have changed location. I mean the angles have changed size. So those corresponding angles aren't even congruent anymore. As a result, the figures are not congruent. So we're just making that little bit of a comparison between the sides of two triangles versus the sides of some other shape. So in our congruence unit, as we're looking at the topic of congruence, we're going to be pretty much just working with triangles because that's where the shortcuts occur. That's where we can use the special patterns. If we don't have triangles, then we're back to using the original idea, which is compare every pair of corresponding sides and every pair of corresponding angles. And so our shortcuts only work with triangles. So let's use that now in example 1 as we take a look at determining if the congruent statement is true. This is true or false. In other words, are they actually congruent triangles or are they not congruent triangles according to the congruent statement? So we're claiming that triangle JKL is congruent to triangle MKL. Now you can see the numbers match up, the 9 with the 9, the 8 with the 8, but you have to make sure that the corresponding parts are the ones that we see with the 8s and with the 9s. So again, look at the first two letters, J and K, that's an 8. That should pair up with M and K, which is also an 8, so that's good. Alright, so the next two letters, KL and KL, there's no number there, but it's a shared side. And you may remember that if we have two triangles sharing a side, then that means that both triangles have the exact same side length, and we're allowed to put a tick mark there because that's the reflexive property. Each triangle has a side of length LK, and so they overlap each other and they are the same length. You look at the first and third letter, and that's JL, that's length 9, and that would correspond with ML, which is also 9. So yes, we do have 3 pairs of sides that are corresponding and congruent. So is this true or false? It is true. We can say yes, it is a true statement, and explain your reasoning. So we want to make sure we understand that segment KL is congruent to itself because one of these comes from the left triangle and the other comes from the right triangle, and we say they are congruent by the reflexive property of congruency, POC. That's how we know all 3 of them. All 3 pairs of sides are congruent. So we would say the triangles are congruent by reason of side, 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 SSS, which represents that side, side, side congruence postulate. Alright, here's part B. So again, we want to know, is this statement true? Are these 2 triangles actually congruent or not? And so the first 2 letters are R and S. That's the side on the left. Here that should pair up with T and V, which is this side on the bottom. So there's no markings here. They may be corresponding, but we don't know if they are congruent. And because we don't know if they are congruent, then the answer is no. We just don't have enough information. We have a pair of sides with a double tick mark. We have a pair of sides with a triple tick mark. That just would be a side side, if you're counting number of sides that are marked up, side, side, we need side, side, side. We need 3 pairs of sides, and we only have 2 pairs of sides here. So no, they are not congruent because there are only 2 pairs of congruent sides in this case, and of course we need 3 pairs. Alright, take a look at part C. Here we have triangle DFG congruent to triangle HKJ. Is that true or false? What do you think? Look at the markings on the diagram. Would you say true or false? So you got to watch out for this one. It's a little bit of a trick question. These are not congruent, and we want to talk about why. So it's, again, commonly when I ask my students in class, they say yes, they are congruent because look, you've got a pair of single tick marks, you've got a pair of double tick marks, you've got a pair of triple tick marks. That's clearly side, side, side. And yes, but that's not the question. The question is not asking, does the diagram show that the triangles are congruent? The question is asking, decide if the congruence statement is true or false. You have to ask, does this diagram match the statement? And it doesn't. Let's see why. The first 2 letters here are D and F, which is on, D and F, which is on the left-hand side with the double tick mark. That should match up H and K. Wait, that's on the bottom with the single tick mark. So in other words, what we see here is that this congruent statement is not written correctly. So if I were to write it correctly, I would instead say triangle DFG is congruent with triangle HJK. They got the order of the letters mixed up. So the statement is false, even though the diagram looks valid. Okay, here's the last one in this series. So triangle ABC congruent with CDA. Take a look at the diagram and what do you think? Is the statement true or false? Right away you see a pair of numbers that appear to be different. You have a pair of 7s, so that looks like a pair of congruent sides. The 2 triangles share here a segment AC with the 9, so you have a 3 and a 4, so that's noticeably different. And so here the statement can't possibly be true if the numbers are not correct. So the answer is no, the statement is false, and that's because segment AB is not congruent with segment, I think that's the letter D down there, segment CD. Okay, so let's take a look at a few more examples on the next page. Here at the top, we'll be graphing these points to create these 2 triangles, and we're asked the question, use the given coordinates to determine if the triangles are congruent. So yes or no, are the triangles congruent? Now again, we have to use this pattern of side, side, side. We have to have 3 pairs of sides, and we have to be able to compare those 3 pairs. So we're not looking at the angles, we're focusing on the sides. And let's start by plotting these points. So A is at -5, 1, 5 to the left, and 1 up. There's point A. B is at -5, 3, 5 to the left, and 3 up. And C is at -1, +1. There's triangle ABC. Alright, so the next triangle contains points D, E, and F, so D is at 2, -2. E is at 4, -2. And F is at 2, -6. Now you might be able to look at them and just kind of eyeball it and say, yeah, I think they're the same, but that's not good enough. You're not allowed to just eyeball it. If we're using this new pattern of the side, side, side pattern, you must show that there are 3 pairs of sides where each pair is congruent. Now, if we're on a coordinate grid, well then we can count the length of vertical lines and horizontal lines. So for example, segment AB is a length of 1, 2. And segment AC is a length of 1, 2, 3, 4. But if it's a slanted line, I cannot count that. We need to use our distance formula to calculate the length of BC. And we will do that in just a moment. With the second triangle on the right, segment DE is horizontal, so we can count that, and that is a length of 2. The vertical side is a length of 1, 2, 3, 4. So far, it looks like we're on the right track. I see 1 pair of congruent segments of length 2, a second pair of congruent segments of length 4. The question is, what about that third pair? So we need to know the length of EF. So we're going to use our distance formula, calculate these 2 lengths, and then we will have that third pair of sides information to be able to determine if the triangles are in fact congruent or not. So here we're calculating the length from B to C, so we're using these coordinate points here. Take the square root of, subtract those x coordinates, so -1 minus -5, wrap that in parentheses and square that, plus. Now subtract those y coordinates. We have a y coordinate of 1 minus the y coordinate of 3, and square that. Let's simplify. So remember, when you are subtracting a negative, that's the same as adding a positive. And so under the radical we have a -1 plus 5. So -1 plus 5, that gives us 4, and I'll square that in a moment. 1 minus 3 is a -2, and I'll square that in a moment as well. So that means we have, under the radical, 4 squared, which is 16, and a -2 squared. Do you remember what that is? Is it +4 or -4? It's a +4. Remember, every time you square something, it's always a positive result. And that gives us a result of root 20, square root 20. Now we can reduce this radical, but for purposes of this example, I'm not going to reduce it. We'll just leave it as square root 20, because all we want to know is, will we have the same result on both of these triangles' slanted sides? The length from E to F then, square root of, those x coordinates are 2 and 4, so 2 minus 4, square the result, add to that. Subtract those y coordinates. We have a -6 minus a -2. So again, turn that into adding a positive, and we'll square that result. So that gives us a result of, so 2 minus 4 is -2, so I've got a -2 that I need to square. -6 plus 2 gives me -4. I need to square that as well. And again, when we square something, that always turns positive, so you have a 4 plus 16, and that gives you a root 20. So yeah, you can see that now the lengths on those slanted sides are the same, root 20. So now we have 3 pairs of congruent sides. So we say, yes, triangle ABC is congruent with triangle DEF. Now if you say that, you have to explain why. Why? By the side congruence postulate, and that's our abbreviation, by SSS. So here we showed that 2 triangles were congruent by looking at their numbers, but if we take away the numbers and we just look at naming the triangles by their parts, we then end up with a 2-column proof. So what you just did up here is actually a kind of a proof. It's called a coordinate proof, using the coordinates to calculate the lengths of sides. So it's not a 2-column proof, but we did prove it. It is a type of proof, but we're going to be spending a lot of our time here in the days to come looking at what do we do if we don't have numbers. How do we prove if these 2 triangles are congruent or not? So I'm looking at these 2 examples, example 3 and 4, with just a couple of shorter proofs to kind of show you what we need to do to show that 2 triangles are congruent. Now remember that our goal here is to use the pattern. The only pattern we have so far, the shortcut, is this side pattern. So that means when I'm looking at these 2 triangles, what I'm needing to do is focus on the sides. We can ignore the angles for now. So given this information and the fact that we have a midpoint, let's focus on the sides and see if we can find 3 pairs of sides that are congruent. Because if we can find it, then we can prove the triangles are congruent. It's also very important, especially in the days to come, it's very important that we mark up the figure as we go along with the proof, so we can keep track of if we actually found all the information on the sides or not. Well, we have some given information here. Segment WX is congruent with segment YX. We wrote it down, so we have to mark it on the diagram. Segment WX is on the left-hand side. That's congruent with YX. So I gave that a pair of tick marks. We're also told that Z is the midpoint. Of segment WY. Alright, so if I'm going to mark that, I'm just going to make a note saying, hey, there's point Z, and I know it's a midpoint. So that's all we have been given to us. But we've studied midpoints in the past. What does the midpoint do to segment WY? It cuts it in half, because the midpoint is in the middle. That means from W to Z, and then from Y to Z are 2 congruent halves, with Z smack dab in the middle. So because I've marked it because we knew we had a midpoint, but because I've marked it, now I have to name it in the proof. We're saying that the segment from W to Z is congruent with the segment from Y to Z. Okay, how did we know that? We knew that because we had a midpoint. So remember, because we made that conclusion from the midpoint, we're going to create an if-then statement where the if part comes from Z is a midpoint, and the then part comes from those 2 segments we just marked up. So let's write an if-then statement. So if a point is a midpoint, then it forms 2 congruent segments. So again, did we make that up? Where did that phrase come from? Remember, that is the definition of a midpoint. So if you prefer, you can just write down the official title, Definition of Midpoint, that communicates the same idea. It's by the definition of a midpoint that we could reason our way into understanding that these 2 segments are congruent. So we have now 2 pairs of sides. What about the third pair? What about this side from X to Z? So again, recall that if you have 2 triangles that are overlapping each other right here, then what you really have going on, I'm going to outline these triangles in 2 different colors. Here you have the left triangle, here you have the right triangle, and they happen to overlap each other here at XZ, then that means the left-hand triangle, whose side is from X to Z, and the right-hand triangle, whose side is also from X to Z, must be congruent. So using my little color coding here, the left side is in red. What we're saying is that the segment from X to Z and the segment from X to Z that came from those 2 different triangles are congruent. Now it looks like it's just the same name both times, but they came from 2 different triangles. But because it is the same name, that's our reflexive property of congruency, POC. Now, if we're going to show the 2 triangles are congruent, we need to see if we have side, side, side. Meaning, do we actually have 3 pairs of sides that are congruent? Yes, you can see it marked in the diagram, but more importantly, do you have it listed over here in the proof? What was given to us was the first pair of sides, number 1. Then, with the midpoint, we found a second pair of sides. Then with the reflexive property, we found a third pair of sides. Once you get all 3 pairs of sides written down by their name, that's when you know the proof is done. That is to say, the final goal of what we're trying to prove can now be declared as true. Triangle WXZ is congruent with triangle YXZ. How do we know? By the side-side-side congruence postulate, because we have 1, 2, 3 pairs of congruent sides. That was a 4-step proof. Here it's even shorter, only 3 steps, and that's just because we have more given information here, keeping it on the short side. So let's write this down. Segment IJ is congruent with segment HK. Okay, you named it, now mark it. Segment IJ and HK, I'm giving a single tick mark. Then in the second piece of given information, segment IH is congruent with segment JK. Alright, you've named it, now mark it. So segment IH, JK, I've given a double tick mark. Of course, that's given. Well, if you think about it, we have our first pair, there's our second pair. How many do we need? We need 3 pairs. There's the shared side. Anytime you have 2 triangles sharing a side, that's another pair of congruent parts. So here is segment JH congruent with segment JH, and that's your reflexive property of congruency, and that provides the third pair of congruent sides. So once you have all 3 named, that's when you know that you're done with the proof. You can now state what we were trying to prove, that triangle HIJ is congruent with triangle JKH, and the reason is side, side, side. These proofs are fairly basic because we're just focusing on sides and there's only one pattern, but they will become more complex in the days to come simply because we're going to have more patterns to consider. Some patterns will use a combination of sides and angles, but this is a key part to help yourself out with any proof. Count off the number of congruent parts that you will need to make sure you have 3 before you can then finish off the proof. All of our shortcuts will have exactly 3 items that are needed. If you only have 2, then that tells you you're missing something. Go back to the diagram and look to see what you can find. Once you've got all 3, that's when you know you can wrap it up and identify the pattern.